In this video, we're going to talk about a type of relation called a total order. All right, so first let's talk a little bit about relations. So recall that if A and B are sets, then a relation between A and B is just a subset of the Cartesian product A cross B. All right, so a relation R is just a set of ordered pairs, subset of A cross B. If A is equal to B, so it's just a subset of A cross A, then we'll say the relation R is a relation on A. All right, now, even though a relation is a set of ordered pairs, instead of writing that the ordered pair A comma B is an element of the relation R, usually we'll write that as A is related to B, A R B, and read it as A is related to B. Okay, we'll see that a lot below when we're talking about total orders. So a few definitions related to relations. First of all, we say a relation is reflexive if everything in the set is related to itself. Okay, so for all little a in big A is related to A. That means the relation is reflexive. A relation is symmetric whenever A is related to B, B is related to A. Okay, so A related to B implies B related to A. That means symmetric. A relation is transitive whenever if A is related to B and B is related to C, then A is related to C. Okay, that's called transitivity. And finally, there's another definition. We say a relation has trichotomy when for all A and B and A, exactly one of the following hold. Either A is related to B, or B is related to A, or A is equal to B. Okay, now notice trichotomy is saying that you can't have two of these holding at the same time. Now that in contrast to symmetry, where if A is related to B, then B is related to A. All right. So trichotomy and symmetry are incompatible. In particular, that means no relation can be symmetric and also have trichotomy at the same time. All right. So finally, we get to the definition of a total order. So if A is a set, a relation on A is a total order when it's transitive and has trichotomy. All right. So it has transitivity and has trichotomy. And when a relation is a total order, we represent it with the less than symbol. Now, if U is a set with a total order and A is a subset of U, we say that an element M of U is a lower bound of A if M is less than or equal to every element of A. All right, so if X is in A, then M is less than or equal to X. That makes it a lower bound of A. Okay, so let's look at this example. We have an interval in the real numbers, all the real numbers between -1 and 1, not including -1 and not including 1. All right, now -1 is a lower bound of that set, and -1 is not a member of that set. Okay, same goes for -2, -3, -5, -10.5. All right, -pi. Those are all lower bounds of this interval, and none of them are elements of the interval. Okay, so a lower bound does not have to be a member of the set. But a lower bound might be a member of the set. If we modify this interval to be the interval from -2 to 2, but also say we're only looking for integers between -2 and 2, then of course that works out to be the set containing the integers -1, 0, and 1. Now, -1 is a lower bound of that interval. Okay, but -1 is also an element of that interval. Okay, so this example illustrates two things. One, it illustrates that lower bounds may or may not be in the sets that they're lower bounds for, but it also illustrates, of course, that the interval notation is ambiguous, and you better be clear about what set the interval is a subset of in order to understand its properties. Okay, there are also upper bounds. So if U is a set with a total order and A is a subset of U, we say M is an upper bound of A when M is greater than or equal to every element of A. So if X is an element of A, then X is less than or equal to M. All right, so let's consider this interval from -1 to 1, where we do not include -1, but we do include 1. 1 is an upper bound of that interval, and 1 is an element of that interval. Okay. 2 is an upper bound of that interval, but 2 is not. Okay, so again, upper bounds, they might be elements of the set, they might not be elements of the set. Okay. The only thing is an upper bound has to be greater than or equal to everything in the set. Okay, now we can define the minimum of a set. So if U is a set with a total order and A is a subset of U, we say M is a minimum of A if it's an element of A and it's a lower bound of A. Okay, so minimum is just a lower bound that's also in the set. Okay, now if a minimum of a set exists, so if a set A has a minimum, then it's unique. There's only one minimum. And since it's unambiguous, we can write M is equal to the min of A. So look at this interval. It's now the closed interval from -1 to 1. All right, so it's all of the real numbers including -1 and including 1. -1 is a lower bound of that set and also an element of that set. Okay, so we'd write -1 is the min of that closed interval. Notice that the interval from the open interval from -1 to 1, it just has no minimum. It has lower bounds, but it has no minimum. Okay, and I noticed there in that set definition, it should be -1 less than or equal to x, less than or equal to 1. All right, it's a closed interval, so we want to include -1 and 1 as we said in the discussion. Okay, what about a maximum? So we say that an element is a maximum of a set A if it's an upper bound and a member of the set. So just like minimums are lower bounds that are elements of the set, maximums are upper bounds that are also elements of the set. Okay. So if a set has a maximum, then it's unique, just like with minimums. And in that case, we write M is equal to the max of A. All right. So again, let's look at this closed interval from -1 to 1. So it's all real numbers that including between -1 and 1 and including -1 and 1. Here, as we said earlier, -1 is the minimum of that interval, and of course 1 is the maximum of that interval. Okay. Again, the interval -1 to 1 open, where we do not include -1 and do not include 1. Now here this interval has upper bounds, but it has no minimum and no maximum. All right. But if we look at the set like the set of integers -1, 3, and 5, that has a minimum of -1 and a maximum of 5. Okay, so just some examples of mins and maxes. 10, notice, is an upper bound of the set A that's not a maximum, and 0 is a lower bound that's not a minimum. Okay, so maximums are upper bounds, but not all upper bounds are maximums. Minimums are lower bounds, but not all lower bounds are minimums. Okay, sets may or may not have minimums or maximums. They may or may not have upper bounds or lower bounds. But if they have a max, they have an upper bound. If they have a min, they have a lower bound. Okay, so now we're going to define the concept of an infimum of a set. So essentially, infimum is just it's just the greatest lower bound, really. Okay, but we define it slightly differently. Let's let U be a set with a total order. If A is a subset of U, we say M is an infimum of the set A if, first of all, it's a lower bound. So M is less than or equal to everything in A. That is, if X is in A, then M is less than or equal to X. Okay, so an infimum is a lower bound, but it's also the greatest of the lower bounds. And the second clause there says that, in this way, it says if something's larger than M, if it's larger than the infimum, then it's not a lower bound. Okay, so there's something in the set less than it. So if L is greater than M, then there's an X in A such that X is less than L. Okay, so it's an infimum if it's a lower bound and anything larger than it is not a lower bound. Okay, so it's another way of saying it's the greatest lower bound. And we have two theorems with regards to infimums. First of all, if they exist, so if a set has an infimum, then it's unique. So we'll write M is equal to inf of A. But we also have a theorem that says exactly what I was trying to explain when we were going over the definition, that if M is the infimum of A, then it's actually the greatest of all the lower bounds of A. So it's the greatest lower bound. All right, notice that if M is the minimum of a set, then it's also the infimum of the set. Okay, but a set can have an infimum and have no minimum. So for example, the interval, the open interval from -1 to 1 has no minimum, all right? But -1 is what we'd call the infimum. It's the greatest of the lower bounds. Okay, just like infimums, we have supremum. Now supremum is going to be the least upper bound, as we'll see in a minute. So if A is a subset of U and U is a set with a total order, then M is a supremum of A when, first of all, it's an upper bound. So M is greater than or equal to everything in A. In other words, if X is in A, then X is less than or equal to M. And we also want to say that it's the least upper bound. So we want to say if something is smaller, it's not an upper bound. All right. So we can say that by like this. If L is less than M, then there exists an X in A that's greater than L. So X is greater than L. So if something is less than M, it's not an upper bound of the set A because there's something in A greater than it. So that's a definition of a supremum. And we have two theorems related to supremums. The first is that a supremum, when it exists, is unique. So if U is a set with a total order, and A is a subset of U, and M is the supremum of A, then, okay, we have this theorem. It's the least upper bound, as I was saying earlier with the definition. All right. And then also, if A has a supremum, then it's unique. All right. So two theorems about supremums, just like the corresponding theorems for infimums. The supremum is the least of the upper bounds, just like the infimum is the greatest of the lower bounds. And supremums are unique, just like infimums are unique. All right. So notice that if M is a maximum of a set, then M is the supremum. Okay. But a set can have a supremum and have no maximum. So again, this example, the open interval from -1 to 1, that set has no maximum, but the number 1 is the supremum of the set. Okay. One last definition here before we start talking about completeness. Let U be a set with a total order. We say that U is a well-ordered set when if A is a subset of U and A is not empty, then A has a minimum. Okay, so well-ordered says that every non-empty set has a minimum. Okay, so what's an example of a well-ordered set? Well, the natural numbers. We've worked with the natural numbers a lot in this course, and one of its most important principles, as we know, is the well-ordering principle. Okay, so the natural numbers is kind of the canonical example of a well-ordered set. It also happens to be the case that any finite set is well-ordered. Notice that the integers, z, it's not a well-ordered set. So for example, the set of odd numbers has no minimum, as does, z itself. There are a lot of subsets of z that have no minimum. The rationals and the real numbers are also sets that are not well-ordered. Okay, so let's define completeness. So let's say U is a set with a total order. We say U is a complete when every non-empty subset of U, which is bounded below, has an infimum. Okay, so if A is not empty and is bounded below, then there's some element M in U such that M is the infimum of A. Okay, so a set U is complete if non-empty sets which are bounded below have infimums. And of course, the main example of a complete set that we've seen is the set of real numbers. We have this alternate completeness axiom, just like we had an alternate completeness axiom for the real numbers. We have the one that works for complete sets in general. So if U is a set with a total order and U is complete, the following holds. If B is not empty and bounded above, then it has a supremum. Okay, so these are kind of equivalent ways to describe complete sets. One is saying that non-empty sets that are bounded below has infimums, but we're saying it's equivalent to say that non-empty sets which are bounded above have supremums. Okay, so we're going to prove that, and before we do, let's make a definition. We'll say U is a set with a total order, and S is a subset of U. UB of S is going to denote all the upper bounds of the set S. All right. So we have a lemma here about UB of S. So if S is an element of the set S, then S is a lower bound of the set of upper bounds of S. All right. So how do we prove that? Well, we're going to start with an element S in some set S, and we're going to show it's less than or equal to any upper bound of S. All right, which sounds pretty obvious. That's why it's a pretty short proof. Let's suppose S is an element of the set S. So we have to show that for all elements U in UB of S, S is less than or equal to U. Of course, if U is in UB of S, that means that U is an upper bound of S, right? So suppose U is in UB of S. U is an upper bound of S. Well, if U is an upper bound of S, that means that it's greater than or equal to everything in S. In particular, since S is in S, it follows that S is less than or equal to U. Okay, and that's all we have to say. That shows that S is a lower bound of UB of S, because anything you pick in UB of S, S is less than or equal to that. All right. So any element of S is a lower bound of the set of upper bounds of S. All right. So we're going to use that lemma to prove this theorem, the alternate completeness axiom. All right. So we're going to suppose that we have a complete set. We're going to suppose that we have a set U which is complete, which means that nonempty sets which are bounded below have infimums. Then we're going to prove that nonempty sets which are bounded above have supremums. So let's say U is a set with a total order, and let's say U is complete. All right. So we know again that every nonempty subset of U that's bounded below has an infimum. And let's suppose we have a nonempty set that's, instead of being bounded below, it's actually bounded above. Now we need to show that this set has a supremum. All right. So let's look at the set of upper bounds of B. Now B is bounded above, so we know there's at least one upper bound of B. Okay, so UB of B has at least one element. It's not empty. And B itself is not empty. And we know anything in B is a lower bound of the set of upper bounds of B from our previous lemma. So we know that this set, the set of upper bounds of B, has at least one lower bound. Okay? So we know that the set of upper bounds of B is not empty and is bounded below. Well, what does that tell us? By completeness, it tells us that the set of upper bounds of B has an infimum. Okay? Let's call it M. So M is the infimum of the set of upper bounds of B. Well, what does that mean? That means that M is a lower bound of the set of upper bounds of B. So if X is an upper bound of B, then M is less than or equal to X. All right? It also means that it is the greatest lower bound. Okay, so if anything's larger, it's not a lower bound. In other words, if L is bigger than M, then there's an upper bound of B X, so that X is less than L. All right? So we're going to claim that this is actually the supremum of B. So the infimum of the set of upper bounds of B, we claim is actually the supremum of B. All right, well, how do we prove that? Well, we got to prove two things. We have to prove that M is an upper bound of B. All right, and we have to prove, not only that, but we have to prove that it's the least upper bound in the sense that anything less than it is not an upper bound. So we have to prove that, first of all, it's an upper bound. If y is in B, then y is less than or equal to M. And secondly, we have to prove is if L is less than M, then there's something in B, a y in B, greater than L. Okay, so let's prove that M is an upper bound of B. So assume y is an element of B. Let's assume by way of contradiction that y is greater than M. Okay. Now, that means by our second condition that there is something in the upper bounds of B greater than y. Okay. So y is greater than M, sorry, less than y. So y is greater than M, y is greater than the infimum of the set of upper bounds of B. And if you're greater than the greatest lower bound, then you're not a lower bound. So there exists something in the set of upper bounds of B less than y. Okay. But wait a minute, x is actually an upper bound of B, okay, because it's in UB of B. So that means, since y is in B, that y is less than or equal to x, right? So then we get that y is less than x and less than or equal to x. So y is less than, x is less than y, and y is less than or equal to x, and so that's a contradiction. Okay. So that proves that M is an upper bound of B. So to prove 2, we have to show that if something is less than M, okay, remember we're trying to prove that M is the supremum of B, so we have to prove that anything less than it is not an upper bound. So we have to show if L is less than M, then there exists a y in B so that y is greater than L. So let's assume that L is less than M. Alright. Now, since M is a lower bound of the set of upper bounds of B, if something is less than M, then it's not in the set of upper bounds of B. Okay. So in particular, L is not in the set of upper bounds of B. Okay. Well, that means L is not an upper bound of B. So there has to be an element of B that prevents this, right? In other words, there has to be a y in B with y greater than L. Alright, so that finishes the proof of 2. That shows that if L is less than M, there's an element y of B so that y is greater than L. Right? So we've proved that two things. We've proved that M is an upper bound and that it's the least of all the upper bounds. Okay? In other words, we've proved that M is the supremum of B. And that finishes this video. Thanks for listening.